Imagine a galaxy whose light has crossed the universe for over 13 billion years, revealing a cosmos less than 500 million years old, so distant, so ancient, it challenges everything we thought we knew about the early universe. This discovery, made possible by the James Webb Space Telescope, has astronomers rethinking the timeline of galaxy formation. How could such a massive structure exist so early in the universe's history? And what secrets does this ancient light hold about the birth of stars and the first galaxies? As we peel back the layers of time, one thing is clear: the early universe was far more complex than we ever imagined. This object isn't just a distant speck, it's a time capsule, offering a rare look at the cosmos in its infancy. What we find could rewrite our understanding of how the universe evolved, and perhaps even where we came from. In the vast expanse of the cosmos, where light travels across billions of years to reach our eyes, astronomers have made a groundbreaking discovery. Using data from the James Webb Space Telescope, they've identified an object that dates back to the earliest moments of the universe, just a few 100 million years after the Big Bang. This finding offers a rare glimpse into the universe's infancy, revealing how the first galaxies and stars might have formed under conditions we've only begun to understand. But how did they find such an ancient object, and why is it so significant? Let's explore the story behind this discovery. The James Webb Space Telescope, launched in 2021, is designed to peer into the universe's distant past. Unlike its predecessors, Webb's advanced infrared instruments allow it to detect light that has been stretched over time, a phenomenon known as redshift. When light from a distant object travels through space, it stretches into longer wavelengths, shifting toward the red end of the spectrum. The more distant an object, the greater its redshift. By measuring this shift, astronomers can determine how far away an object is and, crucially, how long its light has taken to reach us. This is how scientists estimate the age of the universe's earliest structures. The object in question, recently announced by an international team of researchers, is among the most distant galaxies ever observed. Its light has traveled over 13 billion years to reach us, meaning we're seeing it as it appeared when the universe was less than 500 million years old. This period, known as the Cosmic Dawn, is a critical era in the universe's history. It was during this time that the first stars and galaxies began to form, illuminating the dark expanse of the cosmos. However, studying this epoch has always been challenging because the light from these ancient objects is faint and obscured by cosmic dust. Webb's infrared capabilities have now made it possible to peer through this veil, revealing details previously hidden from view. The discovery was made by analyzing data from Webb's near-infrared camera, NRC, which captures images in the infrared spectrum. The team identified a faint but distinct light source that stood out against the backdrop of the universe. Initial observations suggested the object was extremely distant, but further analysis confirmed its age. By measuring the redshift of its light, the researchers determined that it existed just a few 100 million years after the Big Bang. This places it in the earliest stages of galaxy formation, a time when the universe was still largely dark and filled with primordial gas. What makes this object particularly intriguing is its brightness. Despite its immense distance, it appears brighter than expected, suggesting it may have formed under unique conditions. Some theories propose that the first galaxies were massive and luminous, forming rapidly from dense clouds of gas. This object could be one such galaxy, providing clues about how these early structures grew and evolved. However, the exact nature of the object remains a subject of study. Is it a massive galaxy, a cluster of young stars, or perhaps a quasar, a supermassive black hole actively consuming gas and emitting intense radiation? The answer could reshape our understanding of how the universe's first luminous objects came to be. The significance of this discovery lies in its potential to answer fundamental questions about the universe's origins. For decades, scientists have debated how the first galaxies formed. Did they build up gradually from smaller structures, or did they form rapidly in a burst of activity? The existence of this object suggests the latter. If it is indeed a massive galaxy from the cosmic dawn, it would imply that some of the universe's earliest structures formed much more quickly than previously thought. This challenges existing models of galaxy formation and highlights the need for new theories to explain these early cosmic phenomena. Moreover, this object offers a window into the role of dark matter in the early universe. Dark matter, which makes up most of the universe's mass, is thought to have played a crucial role in the formation of galaxies by providing the gravitational scaffolding for gas to collapse into stars. However, the distribution and behavior of dark matter in the early universe remain poorly understood. By studying objects like this, astronomers can test theories about how dark matter interacted with ordinary matter to shape the cosmos. The presence of such a luminous object in the early universe may indicate that dark matter was more concentrated in certain regions, facilitating the rapid formation of massive structures. Another key aspect of this discovery is its implications for the study of star formation. The first stars, known as population 3 stars, are thought to have been massive, short-lived, and composed almost entirely of hydrogen and helium. These stars would have been incredibly bright and hot, but their light would have been difficult to detect due to the vast distances involved. The object in question, however, appears to emit light that is consistent with the presence of young, massive stars. This suggests that the conditions for star formation in the early universe were different from what we see today, possibly involving higher densities of gas and different chemical compositions. The discovery also raises questions about the role of cosmic inflation and the distribution of matter in the early universe. Cosmic inflation is a theory that explains how the universe expanded rapidly in the first fractions of a second after the Big Bang. This expansion would have created tiny fluctuations in the distribution of matter, which later became the seeds for galaxies and large-scale structures. The presence of such a massive object in the early universe could provide insights into the initial conditions of these fluctuations and how they evolved over time. By studying the properties of this object, scientists can test whether the universe's structure formed in a way consistent with inflationary models. Despite these exciting possibilities, the study of such distant objects is not without challenges. The light from these ancient structures is incredibly faint, requiring advanced instruments like Webb to detect it. Even with Webb's capabilities, the data must be carefully analyzed to distinguish between genuine signals and background noise. The team of astronomers involved in this discovery spent months processing and interpreting the data, using sophisticated algorithms to isolate the object's light from the surrounding cosmic background. This meticulous work underscores the importance of technological advancements in expanding our understanding of the universe. In addition to its scientific implications, this discovery has profound philosophical and existential significance. It reminds us that the universe is vast, ancient, and full of mysteries waiting to be uncovered. Every new observation brings us closer to understanding our place in the cosmos, yet it also highlights how much remains unknown. The fact that we can now peer back to within a few 100 million years of the Big Bang is a testament to human ingenuity and the power of scientific exploration. It also raises questions about the future of our universe: how will it evolve, and what other secrets lie hidden in the depths of space? As researchers continue to analyze the data from this object, they may uncover new insights that could revolutionize our understanding of the early universe. This discovery is not just a milestone in astronomy, it is a reminder of the enduring curiosity that drives scientific inquiry. By looking back at the universe's infancy, we gain a deeper appreciation for the processes that shaped the cosmos and, ultimately, our own existence. The journey to uncover these secrets is far from over, but with tools like the James Webb Space Telescope, the possibilities for discovery are boundless. The universe is a vast, ancient expanse, its history written in light that has traveled billions of years to reach us. For decades, astronomers have peered into the cosmos to unravel its origins, searching for clues about the first stars, galaxies, and the forces that shaped them. But until recently, the early universe remained shrouded in mystery, its distant, faint objects too dim and distant to be observed with the tools of the past. Now, a new discovery has pushed the boundaries of what we can see, revealing an object from the universe's earliest days, hidden in the cosmic dark. This is the story of how scientists, using the James Webb Space Telescope, uncovered this ancient relic, and what it means for our understanding of the cosmos. The journey began with the James Webb Space Telescope, a marvel of engineering and ambition. Launched in 2021, Webb was designed to observe the universe in infrared light, a wavelength that allows it to peer through the cosmic fog of interstellar dust and detect the faint glow of objects formed just a few 100 million years after the Big Bang. Unlike its predecessors, such as the Hubble Space Telescope, which primarily observes visible and ultraviolet light, Webb's instruments are optimized to capture the faint, redshifted light of distant galaxies. This makes it uniquely suited to study the early universe, where the first stars and galaxies were born. At the heart of this discovery were two of Webb's key instruments, the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI. These tools work in tandem to capture detailed images and spectra of celestial objects. NIRCam, with its high-resolution imaging capabilities, was used to detect the faint, distant light of the object, while MIRI provided crucial data on its chemical composition and temperature. Together, they allowed scientists to gather a comprehensive picture of the object's properties, even though it was so far away that its light had taken over 13 billion years to reach Earth. The process of discovery was not immediate. It required a careful, methodical approach, beginning with the collection of vast amounts of data. Webb's sensors continuously recorded the light from distant regions of the universe, capturing images that would later be analyzed by teams of astronomers. These images, however, were not immediately revealing. The object in question was so faint and distant that it appeared as a faint smudge in the early datasets. To identify it as a genuine astronomical object, scientists had to apply sophisticated algorithms to filter out noise, distinguish it from other sources of light, and determine its true nature. One of the most critical steps in this process was the analysis of the object's light spectrum. By studying how the light from the object was absorbed and emitted, scientists could determine its composition and age. This is where MIRI played a vital role. The instrument's ability to detect mid-infrared wavelengths allowed researchers to measure the object's redshift, a key indicator of its distance. Redshift occurs because the universe is expanding, stretching the wavelength of light as it travels through space. The higher the redshift, the farther away the object is, and the older it is. By calculating the redshift, scientists could estimate the object's age, placing it in the universe's infancy, just a few 100 million years after the Big Bang. But confirming the object's existence was not just a matter of analyzing data. It required multiple observations over time to ensure the findings were reliable. Astronomers used Webb's instruments to capture images of the same region of the sky at different times, allowing them to track changes and rule out the possibility of instrumental errors or transient phenomena. This iterative process, often spanning months or even years, is a hallmark of astronomical research. Every observation added another layer of evidence, building a case that the object was not just a random fluctuation in the data but a real, distant celestial body. The significance of this discovery lies in what it tells us about the early universe. The object, which scientists have since named GN101384, though the exact name may vary depending on the source, is believed to be one of the first galaxies to form. Such galaxies are thought to have played a crucial role in shaping the universe's structure, providing the seeds for the vast cosmic web of galaxies we see today. By studying these ancient objects, astronomers can gain insights into the processes that led to the formation of stars, the assembly of galaxies, and the evolution of the universe itself. However, the discovery was not without challenges. The faintness of the object meant that even with Webb's advanced technology, the data required careful calibration and interpretation. Scientists had to account for various factors, such as the background light from other galaxies, the effects of interstellar dust, and the potential for measurement errors. These challenges underscore the complexity of astronomical research, where even the most advanced instruments require meticulous analysis to extract meaningful results. Another critical aspect of the discovery was the collaboration between different research teams. The work of identifying and confirming the object involved astronomers from around the world, each contributing their expertise in different areas. Some focused on data analysis, while others specialized in theoretical modeling or observational techniques. This collaborative effort highlights the nature of modern astronomy, where discoveries are often the result of collective effort rather than individual achievement. The implications of this discovery extend beyond the object itself. It represents a milestone in our ability to observe the early universe, opening new avenues for research. With Webb's capabilities, scientists can now study similar objects in greater detail, potentially uncovering more about the conditions that existed in the universe's infancy. This could lead to a deeper understanding of the fundamental forces that governed the cosmos in its earliest moments, as well as the processes that led to the formation of the first stars and galaxies. As the data from Webb continues to be analyzed, it is likely that more such discoveries will emerge. Each new object found in the early universe adds another piece to the puzzle of cosmic history, helping us piece together the story of how the universe evolved from a hot, dense state to the vast, structured cosmos we observe today. The journey of discovery is far from over, and with every new observation, we come closer to understanding the origins of everything that exists. Astronomers find a new object from the early universe using Webb data. This part of our deep dive into Astronomers Find a New Object from the Early Universe Using Webb Data focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. Astronomers find a new object from the early universe using Webb data. This part of our deep dive into Astronomers Find a New Object from the Early Universe Using Webb Data focuses on, give historical context, how our understanding of this general topic evolved over past decades, earlier missions, or discoveries that led up to this moment. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. The discovery of this new object from the early universe has ignited a wave of curiosity and debate among astronomers, revealing just how much we still have to learn about the cosmos. While the James Webb Space Telescope has already transformed our ability to peer into the distant past, this find raises profound questions about the origins of the universe and the processes that shaped it. At the heart of the mystery is the object's very existence. How could such a massive structure have formed so quickly after the Big Bang? Current theories suggest that the early universe was a chaotic, rapidly evolving environment, but the speed at which this object emerged challenges existing models of star and galaxy formation. Scientists are now grappling with the implications of this discovery, as it forces them to reconsider the timeline of cosmic evolution and the role of dark matter, gravity, and other unknown forces in shaping the universe. Yet, even as they work to unravel these mysteries, there are still many unanswered questions. For instance, what exactly is this object? Could it be a star, a galaxy, or something entirely new? And if it is a galaxy, how does it fit into the broader picture of how galaxies formed and evolved in the early universe? These uncertainties highlight the complexity of the task ahead, as astronomers strive to reconcile this discovery with the vast body of existing knowledge. The object's distance from us is another critical factor.
Because light from such distant objects takes billions of years to reach Earth, we are essentially looking back in time, observing the universe as it was in its infancy. However, determining its exact distance and age remains a challenge. Astronomers rely on redshift measurements to estimate these values, but even the most advanced instruments can struggle with the precision required for such ancient objects. The data from the James Webb Space Telescope has provided valuable insights, but there is still room for error, and the object's true nature may not be fully understood until further observations are made. Moreover, the object's composition is a subject of intense interest. If it is a star, its metallicity, its abundance of elements heavier than hydrogen and helium, could offer clues about its formation. Early stars were thought to be metal poor, but if this object has a different composition, it could indicate new pathways for star formation that were previously unknown. However, without more detailed spectral analysis, these possibilities remain speculative. The scientific community is also divided on how to interpret the object's significance. Some researchers argue that it could be a rare but natural variation of existing astrophysical processes, while others believe it represents a fundamentally new phenomenon that defies current understanding. This debate underscores the dynamic nature of scientific inquiry, where each discovery opens new avenues of exploration and challenges existing paradigms. Another layer of complexity lies in the object's potential role in the early universe's structure. If it is a massive galaxy or a supermassive black hole, it could have played a crucial role in shaping the distribution of matter in the cosmos. However, the mechanisms by which such structures formed in the early universe are still poorly understood. Theories about the formation of supermassive black holes, for example, suggest that they may have formed through the direct collapse of gas clouds or through the rapid accretion of material in the first dense regions of the universe. If this object is related to such processes, it could provide critical evidence to support or refute these theories. Yet, without more data, these ideas remain hypotheses rather than confirmed facts. The broader implications of this discovery extend beyond the object itself. It raises questions about the overall timeline of cosmic evolution, including the rate at which galaxies formed and the role of dark matter in their development. The early universe was a period of rapid change, with galaxies forming in a relatively short timespan compared to the billions of years it took for structures to evolve in later epochs. This object's existence could challenge or refine our understanding of these processes, potentially revealing new insights into the interplay between dark matter, gas dynamics, and star formation. However, these questions are not easily resolved. The complexity of the early universe means that many factors could have contributed to the object's formation, and isolating the key variables remains a significant challenge. Scientists must also consider the possibility that this object is an outlier, a rare anomaly that does not represent a broader trend. While such anomalies are valuable for pushing the boundaries of our knowledge, they also highlight the limitations of current models. The object's discovery has also sparked discussions about the future of observational astronomy. As instruments like the James Webb Space Telescope continue to provide unprecedented data, they will undoubtedly lead to more such discoveries. However, the sheer volume of data and the complexity of analyzing it mean that many questions will remain unanswered for years to come. The scientific community is already working to develop new methods for processing and interpreting this data, but the process is as much about refining our tools as it is about uncovering new truths. In this context, the object serves as a reminder of how much we still have to learn about the universe. It is a testament to the power of modern astronomy to peer into the depths of time and space, but also a reflection of the enduring mysteries that lie beyond our current understanding. As researchers continue to study this object and others like it, they will undoubtedly uncover new insights, but the journey will be long and filled with uncertainty. The discovery of this object is not just a milestone in its own right, it is a catalyst for deeper inquiry, challenging scientists to rethink their assumptions and explore new possibilities. In the end, the true value of this find lies not in the answers it provides, but in the questions it raises, questions that will drive the next generation of astronomical research and continue to shape our understanding of the cosmos. As the James Webb Space Telescope continues to unveil secrets of the cosmos, the discovery of this newly identified object from the early universe has sparked a wave of anticipation among astronomers. This find is not just a milestone in itself but a catalyst for future research that could reshape our understanding of the universe's origins. The next steps in this scientific journey involve a series of follow-up observations and the deployment of advanced instruments that will build upon the data gathered by Webb.
These efforts are crucial for confirming the object's properties, extending the implications of its discovery, and potentially challenging existing theories about the formation of the first galaxies and the evolution of cosmic structures. One of the immediate priorities for astronomers is to conduct detailed spectroscopic analysis of the newly discovered object. Spectroscopy, which involves breaking down the light from an object into its component wavelengths, can provide critical information about its composition, temperature, and motion. By analyzing the spectral signatures, scientists can determine the object's redshift, which indicates how far away it is and how long its light has been traveling to reach us.
This data will help confirm whether the object indeed dates back to the early universe, as suggested by its initial detection.
Additionally, spectroscopy can reveal the presence of specific elements and molecules, offering insights into the chemical processes occurring in such distant celestial bodies. These findings could shed light on the conditions in the early universe and the mechanisms that led to the formation of the first stars and galaxies. Beyond the immediate follow-up studies, the scientific community is already looking ahead to future missions and instruments that will complement the capabilities of the James Webb Space Telescope.
One such mission is the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s. This telescope, named after the pioneering astrophysicist, is designed to conduct wide-field surveys of the universe, capturing vast swaths of sky with unprecedented sensitivity.
Its primary mission includes mapping dark energy and dark matter, but its capabilities also extend to the study of distant galaxies and the search for exoplanets. The Roman telescope's ability to capture detailed images of large areas of the sky could enable astronomers to identify more objects like the newly discovered one, potentially revealing patterns or anomalies that further refine our understanding of cosmic evolution.
Another significant upcoming mission is the Euclid Space Telescope, developed by the European Space Agency, ESA. Scheduled for launch in the early 2020s, Euclid will focus on investigating the nature of dark energy and the large-scale structure of the universe. Its advanced instruments, including a high-resolution visible imager and a near-infrared spectrometer and photometer, will allow scientists to map the distribution of galaxies and dark matter across cosmic time. By combining data from Euclid with observations from the James Webb Space Telescope, researchers can create a more comprehensive picture of the universe's expansion and the role of dark energy in shaping cosmic structures. This synergy between missions could help validate or challenge existing models of cosmic evolution, particularly in the context of the newly discovered object's properties. In addition to space-based observatories, ground-based telescopes are also poised to play a vital role in future studies of this object and similar discoveries. The Extremely Large Telescope, ELT, currently under construction in the Atacama Desert of Chile, represents a significant leap in observational power. With a primary mirror spanning 39 meters in diameter, the ELT will be the largest optical telescope ever built. Its advanced adaptive optics systems will allow astronomers to achieve unprecedented resolution, enabling detailed observations of distant objects that are currently beyond the reach of even the James Webb Space Telescope. The ELT's ability to capture high-resolution images and spectra of faint, distant galaxies could provide critical insights into the physical processes occurring in the early universe, including the formation of the first stars and the assembly of the first galaxies. Moreover, the development of new instruments and technologies is expected to enhance our ability to study objects from the early universe. For instance, the next generation of spectrographs, such as the High-Resolution Echelle Spectrometer, HIRS, on the upcoming Giant Magellan Telescope, GMT, will offer even greater precision in analyzing the light from distant objects. These instruments will enable astronomers to detect subtle variations in spectral lines, which could reveal information about the chemical composition, velocity, and other properties of the newly discovered object. Such data will be essential for determining whether this object fits within existing theoretical models or if it represents a new class of celestial phenomena that requires revisions to our current understanding. The study of this object also raises intriguing questions about the nature of dark matter and dark energy, two enigmatic components that make up the majority of the universe's mass-energy content. While the newly discovered object may not directly address these mysteries, its properties could provide indirect clues about the distribution and behavior of dark matter in the early universe.
For example, if the object's gravitational influence is found to be stronger than predicted by current models, it could suggest that dark matter interacts with itself in ways not yet accounted for. Similarly, the object's motion through space might offer insights into the expansion rate of the universe, which is closely tied to the properties of dark energy. Future observations with advanced telescopes and instruments will be critical in exploring these connections and refining our understanding of the universe's fundamental forces. Another area of focus will be the search for additional objects like the newly discovered one, which could help establish whether this find is an isolated anomaly or part of a broader trend. If multiple objects with similar characteristics are identified, it could indicate that certain processes or conditions were more common in the early universe than previously thought. This would have profound implications for theories about galaxy formation, star formation rates, and the overall structure of the cosmos. Conversely, if the newly discovered object proves to be unique, it could challenge existing models and prompt the development of new hypotheses to explain its existence. The ability to detect and study such objects will depend on the continued advancement of observational technologies and the collaborative efforts of the global astronomical community. The potential for future discoveries is also tied to the development of machine learning and artificial intelligence tools that can analyze vast amounts of astronomical data more efficiently. These technologies are already being used to sift through the data collected by the James Webb Space Telescope, identifying patterns and anomalies that might be missed by human observers. As these tools become more sophisticated, they will enable astronomers to process data from future missions more quickly, allowing for faster confirmation of discoveries and more rapid analysis of their implications. This computational power will be essential in handling the sheer volume of data generated by upcoming missions like the Nancy Grace Roman Space Telescope and Euclid, which will produce terabytes of information each day. In addition to technological advancements, the international collaboration among astronomers will play a crucial role in the future study of this object and other discoveries. The James Webb Space Telescope itself is a product of a collaborative effort involving NASA, the European Space Agency, and the Canadian Space Agency, and future missions will likely follow a similar model. This global cooperation ensures that resources, expertise, and data are shared across borders, maximizing the impact of each discovery. The newly identified object, for example, may lead to joint research initiatives between different space agencies and observatories, fostering a more integrated approach to understanding the universe's origins and evolution. As the scientific community continues to explore the implications of this discovery, it is also important to consider the broader context of cosmic history. The early universe was a period of rapid change, with the formation of the first stars, the reionization of the cosmos, and the emergence of large-scale structures. The newly discovered object, if confirmed to be from this era, could provide a unique window into these processes. By studying its properties and comparing them with theoretical models, astronomers can test the validity of current cosmological theories and refine our understanding of the universe's timeline. This research could also have implications for the study of other cosmic phenomena, such as the formation of supermassive black holes and the distribution of dark matter in the early universe. Ultimately, the discovery of this object marks the beginning of a new chapter in the exploration of the early universe. While the James Webb Space Telescope has already provided groundbreaking insights, the future holds even greater possibilities as new missions, instruments, and technologies come into play. The coming years will be defined by a combination of meticulous follow-up studies, collaborative efforts, and technological innovation, all aimed at unraveling the mysteries of the cosmos. As astronomers continue to push the boundaries of what is possible, each new discovery brings us closer to understanding the origins of the universe and our place within it. The journey is far from over, and the next steps in this scientific adventure are as exciting as they are uncertain, promising to reveal even more about the universe's past, present, and future. In the vast tapestry of the cosmos, where light from the earliest stars has traveled billions of years to reach us, astronomers have made a discovery that feels almost like peering through a veil. Using data from the James Webb Space Telescope, they've identified a new object from the early universe, a relic so ancient its light has journeyed over 13 billion years to arrive at our telescopes. This find isn't just a headline, it's a window into the universe's formative years, offering clues about how galaxies, stars, and even the fabric of space itself took shape. But how did they find it? And what does it mean for our understanding of the cosmos? Let's break it down. The James Webb Space Telescope, with its unprecedented sensitivity and ability to detect faint infrared light, has become the key to unlocking the universe's earliest secrets. This new object, located in a region of the sky where the light from ancient galaxies is faint and scattered, was detected through its unique glow, a signature that stands out against the cosmic background. What makes this object remarkable is its extreme distance. Its light, emitted when the universe was less than 1 billion years old, has taken an unimaginable amount of time to reach us. This means we're not just seeing the object as it is now, but as it was in the infancy of time itself. Such discoveries are rare, and this one is particularly special because it challenges existing models of how early galaxies formed. But the significance of this find goes beyond its age. The object's properties, its brightness, its composition, and the way it interacts with surrounding cosmic material could reshape our understanding of the early universe. For instance, the presence of certain elements or the rate at which it's emitting light might hint at the role of dark matter or the processes that fueled star formation in the first galaxies. These are questions that have puzzled scientists for decades, and this object provides a new piece of the puzzle.
It's also a reminder of how much of the universe remains hidden, waiting to be uncovered by instruments like Webb. What's even more fascinating is the collaborative effort behind this discovery. Astronomers from around the world have pooled their expertise, using advanced computational techniques to sift through vast amounts of data. The process wasn't instantaneous, it required months of analysis, cross-referencing observations, and ruling out alternative explanations.
This object wasn't just found by chance, it was the result of meticulous work, driven by curiosity and the relentless pursuit of knowledge. It's a testament to how science thrives on teamwork and the power of technology to push the boundaries of what we can observe. Yet, this discovery also raises new questions. If this object exists, what other hidden structures might be lurking in the cosmic dark? How did such a massive object form so quickly after the Big Bang? And what does its existence tell us about the distribution of dark matter in the early universe? These are the kinds of mysteries that drive scientific exploration, and this find is just the beginning. It's a call to keep looking, to keep asking, and to embrace the unknown. So, what's next? The scientific community is already planning follow-up studies to gather more data on this object. Future observations might reveal even more details about its composition, its environment, and its role in the universe's evolution. But for now, this discovery stands as a milestone, a reminder that the cosmos is still full of surprises. It's a humbling thought that in the span of a few years, we've gone from theorizing about the early universe to finding tangible evidence of its earliest moments. If you've enjoyed this deep dive into one of astronomy's most exciting discoveries, consider subscribing to FactVerse for more explorations of the universe's greatest mysteries. Every day, we uncover new stories that challenge our understanding and inspire wonder. And if you have your own theories or questions about this find, we'd love to hear them. Drop a comment below, because the journey of discovery is never truly complete. The cosmos is vast, and there's always more to learn.